there, and welcome to Taiwan Talk, where we share the stories of people living in Taiwan. I'm Trevor Tortomasi, and joining me in the studio today is Satoki Matsushita, an astrophysicist from Japan. Satoki is a research fellow at the Academia Sinica Institute of Astronomy and Astrophysics here in Taiwan, and has worked on international projects like the Event Horizon Telescope and the Greenland Telescope Project. It was those projects that have helped humanity take its first, and then recently, second, pictures of black holes deep in outer space. We spoke with Satoki last year at the end of 2021, but with new discoveries come new conversations. And Satoki, welcome back to the show.
Thank you very much. I'm very happy to come back here, and thank you for the invitation.
If I could, I would just talk to scientists all the time. So I'm really happy to have you back too. Okay, before we get into this year's news, let's refresh our memories just about black holes and space in general, because there was this project called the Event Horizon Telescope. Mm-hmm. How did that work?
Well, black hole, it absorbs whatever things very nearby. Even the light cannot come back. People usually think it is so black and the space is black, so cannot see. But the thing is that there are many things falling into the black hole. Then that makes a light because it's close to the black hole. It is falling in very fast, and that creates the heat. For example, like the viscosity that when you rub your hands together, that the heat comes up.
It's like space friction.
Space friction,
okay.
Yeah, but in the black hole, so that it's very hot,
okay.
So that emits a light, and that's why that the black hole, if something really goes in, then that black hole will show up as a bright things surrounding, dark shadow, and that is so bright that if you have enough spatial resolution, you can actually image it.
So we're imaging what the black hole is doing to everything around it. Of course, we still can't technically see the black hole.
Exactly.
But this evidence is visual and we can see it.
Yes. The problem is that the size is so small that in the past, we couldn't image it technically. But 2017, radio telescope all over the world make it like the whole Earth as the size of the telescope. And that made it possible to actually image the black hole. That's why that the 2019 M87 black hole image, and this year, Sagittarius A star, the center of our galaxy, we could image it.
So, like you told us in our last interview, putting these gigantic telescopes all around the world and using all of them sort of at the same time to help the whole Earth act as kind of almost one lens to see something so far away.
Exactly.
Otherwise, we wouldn't be able to see it.
No, we cannot.
Okay.
At current technology.
In the
future, maybe more, development comes in.
Yeah, we can see it with our cell phones and the. Yeah, okay.
Well, let's see.
Let's see. Okay, so that's the Event Horizon Telescope project. Was basically turning Earth into a giant telescope.
Yes.
So that first picture was of M87, or the black hole at the center of the M87 galaxy.
Yes.
And how many telescopes were involved in taking that picture?
That time it was 8 telescope.
8 all over the world.
Yeah, all over the world. It was 2 in Hawaii, 1 in US mainland, and 1 in Mexico, 1 in Spain, and 2 in Chile, and 1 in South Pole.
And 1 in Greenland? Or was that different?
Greenland was not joined at that time.
Ah, okay.
2017 observation, we didn't join. 2018, the Greenland telescope also joined.
And you were working at the Greenland telescope?
Yes, but at that time, Greenland telescope is not ready yet. So I was in Hawaii actually using the James Clerk Maxwell telescope, we call JCMT. And I was actually observing using the JCMT at that time, yes.
So to get into this year's news, scientists have managed to compile an image of Sagittarius A. Do you say Sagittarius A star?
A star.
Okay, it looks like when it's written down, Sagittarius A and then an asterisk.
Yes.
We say Sagittarius A star.
Yes.
That's the black hole at the center of our own Milky Way galaxy.
Yes.
It's much, much, much smaller than M87.
Exactly.
But when you look through a telescope, correct me if I'm wrong, because of it's smaller and closer, and M87 is bigger but further away, they kind of both look the same size.
Exactly. So that the Sagittarius star is roughly 1,000 times lighter, but it is 1,000 times closer. So it's happened to be almost the same size as the M87 and the Sagittarius star.
Okay, so I've read that the gas ring, just for size comparison,
Yes.
around Sagittarius A star could fit inside the orbit of Mercury, which is around 60 to 62 million kilometers. How was imaging this Sagittarius A star different from imaging M87?
The key here, well, I would say difficulty here, is that M87, light particle rotating around a black hole, was about a few months. But for the Sagittarius star, it is few tens of minutes only.
Oh,
so
wow, okay.
when we observe, we usually observe for one whole day and integrate to make the image. M87, we can integrate, but Sagittarius star, the rotation speed is roughly a few tens of minutes, so that if you integrate for whole night, it just gets blur because light rotates so fast around the black hole.
Yeah.
That's why M87 we show in 2019. Observation was 2017, so we took 2 years. And then we took 3 more years to show Sagittarius star because this imaging was so difficult.
And you said you were actually observing our Sagittarius A star already in 2017?
Almost the same day we observed together with M87 and Sagittarius star.
Okay, but just compiling that data took 3 more years.
3 more years because of the imaging. We have to make a new imaging technique.
And how did you get around that?
So,
is this something we could understand? Or
well, roughly speaking, since it's changing so fast, so we make sort of average image for one day. And sometimes the strength changes, but we took the average image.
You didn't try to take like one thing every few 10 minutes?
We have those kind of every sort of 10 seconds of data, but it's so dim that we need to integrate to make it the nice image.
Right.
But still that the image changes with time, so that if we integrate for a whole day, then the image is so blurred that we're not sure whether this is true or not. So
right. So just to make this absolutely clear, just in case anyone isn't understanding, because it took me a while to really comprehend too. We're not just taking a picture of this thing. We're taking a million pictures, maybe a billion, I don't know, all around the world at the same time. And you have programs and AIs or?
Not really AI. Well, programs to integrate from the raw data to the image. And the integration itself, the data point is something like 10 seconds. And there's many 10 seconds for like 12 hours of 10-second data. And 8 telescope, everything integrate together into make it one image. But for Sagittarius star, it rotates so fast that we need to make the new technique to make the image. That's took a lot of time. Of course, we always developing a new technique. Ideally, we want to make the video or movie of the how Sagittarius star developing with time. But at this moment,
do you mean like a documentary about the imaging? Or do you mean like you want to take a video of Sagittarius A star?
Video of Sagittarius.
Okay,
how
wow.
We want to make the how light rotating around the black hole, like make a movie with our data.
Dang. Wait, well, is this hard to make one picture? So I guess we'll have to wait a bit.
Yes,
okay.
It's very difficult.
So with this image, what more have we learned from observing a smaller black hole rather than a large one?
Large one. So in the past, when we only have M87 image, some people doubt, is it really common picture? Or the black hole looked like this. But this time, we show the different source and we show the similar image. Even the mass of the black hole is 1,000 times different. Wherever mass of the black hole is 1 million solar mass or 1 billion solar mass, it looks like same, which means that the physics of the black hole is common, which means that so far, Einstein is correct.
So far, yeah. I think every new major scientific discovery in physics is always like, well, he's not wrong yet.
Yes.
Or it's hard to say. I don't know. So for imaging black holes, what's next? You said maybe hopefully make videos in the future, but what's the next step?
Several things we want to do. Of course, I cannot tell anything.
Okay, that makes sense, yeah.
But what we show so far is the 2017 data set. And we already took 2018 data. Now that data includes Greenland telescope, which is very north, so that we expect image will be somewhat sharper compared to the 2017. That's the first thing. So that if it's same, then that tells that the black hole doesn't change so much with time, especially for the M87. It's so massive. It takes few months to rotate around, so that the 1 year difference maybe doesn't change much. Or if change, then what's that means? Also that if image gets sharper, then what's a new thing we can see?
Okay, so we're starting with basic pictures. We might see more details as we get the
more telescope.
Okay.
Yeah.
And getting more telescopes on the Earth would still be a big enough, quote unquote, lens to see something better? Or do we eventually have to get telescopes off of the Earth to help with the imaging?
If we want to see more detail, structure, there are two ways. One, go further. Or second, go to higher frequency. Currently, we observe that 2017, the image is at 220 gigahertz. The cell phone is 5 gigahertz. And, it's
200, I mean, that's a lot of cell phone.
Much higher frequency.
Right.
And if you go much higher, then resolution get better. But going higher frequency is cheaper than the going to the space, because making satellite costs a lot. Space program takes usually more than 10 years from the start to the real launching. Usually 20 years or something.
It sure seems like that, yeah.
Yeah, so currently what we are pushing is to make it higher frequency, hopefully within a few years.
Okay, I have a couple more random questions. What is the smallest black hole that we know about?
Smallest so far, what we know in our galaxy is around 4 or 5 times the mass of the sun. So we call stellar mass black hole. It's different from like M87 or Sagittarius A, which we call that the supermassive black hole. So that is million solar mass or billion solar mass. But now I'm talking about a few solar mass, which is the few times the mass of the sun.
And how many black holes have we observed so far in our galaxy?
In our galaxy, so far we know is around 10-ish, although we haven't imaged it, that the other data set tells that this must be the black hole.
And then are there any black holes that we could see from our backyard? We probably don't have a good enough... you can't see a black hole, but how you can see evidence of black holes?
Well, of course, that the shadow of the black hole, no, you need the Earth-sized telescope. So, but in terms of the black hole related thing is that we call quasar, or QSO. Historically, we call quasi-stellar object.
Okay.
And around 1960s, astronomers found out this very bright astronomical source. It looks like star, but turned out to be, it is really, really far away from our Earth, definitely outside of our galaxy. But it's so bright that it outshined the galaxy itself, and only the nucleus you can see.
So it looks like a star from far away.
Yes.
But then they realize it's really giant.
And it's so bright and so far away, so that the only way to explain the energy source of that brightness is a huge amount of material falling into the black hole. And that one we call 3C273, around near the Virgo. It is the magnitude of around 13 magnitude, which with the backyard telescope, around 6-inch telescope or larger, you can see it by the telescope, by backyard.
It's a beginner's black hole.
Yeah.
Okay, cool. So tying this back to the island of Taiwan, what exactly do you do with Academia Sinica in Taiwan?
Oh, for me, I belong to the Institute of Astronomy and Astrophysics. So currently, I'm the principal investigator of the Greenland Telescope project and also representative of Event Horizon Telescope Taiwan team. And currently, I'm really concentrated on these two things. Well, it's busy enough.
Yeah, I imagine so.
But before that, I was working for all the radio telescope that is currently related to this Event Horizon Telescope, like in Hawaii, in Chile. I lived in Hawaii and Chile some years to make those telescope happen. Now more settled in Taiwan.
Okay.
Yeah.
And
well, sometimes go to Greenland. Yes.
And then when you're managing a Taiwan team, how big is this team in Taiwan that is studying?
Scientist-wise, around 10, and engineer technician-wise, between 20 and 30.
Okay. Wow.
Yeah. The reason why Taiwan is in is that Taiwan has a technology. 20 years ago, when this submarine array, SMA, started, they didn't have. But after 20 years, they learned how to make the telescope, how to make the receivers, how to make the electronics. And now Taiwan is one of the world leading place. That's why I'm here in Taiwan. This Academia Sinica Institute of Astronomy and Astrophysics is one of the world leading institute for
awesome.
This radio technology.
Is that thanks to a lot of the chip making manufacturing technology or just engineering in general?
Engineering in general.
Okay.
Yeah. So they are doing really good job.
That's fantastic. Well, you recently got to talk to schools in Taiwan about your work. Well, we interviewed last year in 2020, end of 2021,
Yes.
and then you got to speak to some kids about science and astrophysics. Like, how did that go?
Actually, the one high school teacher contacted me that I heard the 2021 radio program, ICRT,
nice.
and that she wants me to come to her high school and give a lecture or talk about this black hole that at that time only M87.
Right.
And give a presentation about 1 hour, 1.5 hour presentation in English because my Chinese is terrible. And,
it's okay. It's not easy.
But surprisingly, many high school students could understand my English, and that's
awesome.
Yeah. Of course, some part that teacher helped to translate into Chinese, especially some technical words that not that common for high school kids. But still, it was doing very good.
How do you feel about science education in Taiwan?
From my point of view, well, education itself, I'm not really involved in, so that I cannot tell. But sometimes I can see that some high school student visiting our open house, which is once every year that the Academia Sinica does the open house. And the topic was a black hole, and several tons of high school students came to our institute. And that part, it's good that many students are interested in. But personally, what I feel is that when I go to the bookstore, compared to US or Japan, still not much popular science book in Chinese exist. If I go to Japan or US, always there are science section and so many books aligning. But here it's, except for a really big bookstore, the popular science section is still pretty small, I feel. And I hope now that the astronomy research in Taiwan is growing a lot, so that many universities start to hire astronomers, so that those kind of people write technical astronomy book or popular science, astronomy science book. Either is fine, but those kind of books in own language is, I think, important, especially for the junior high school students, or even the undergrad university students to read and learn what's the current latest research in astronomy, or even the whatever science. And I hope that makes changes.
Yeah, I hope we can see changes there soon. I find myself thinking, what if we just hired a bunch of people who are, bilingual English and Chinese speakers to put more subtitles on all the videos and educational content that is already out there in English or in Japanese? You're right, it really does take bringing it into this country's language for people here to truly feel connected to it and understand it. And so once we can pass that language barrier, I think the information is already out there.
Yes, exactly.
Yeah. So that's good to hear. What would you say is some good advice for someone starting out on their science astronomical journey?
Well, I also told that the high school student when I give a talk, of course, most important thing is that you have to be interested in science. And for study, then probably 3 things: physics, math, English. Those 3, the physics and math is so close together, so that those 2 have to be connected. And English, because English is so common language for the whatever world. And once you can speak English, you can access to a lot of people, videos, books. Personally, those 3 I suggest to learn if you want to be the scientist. Basically, all the international conference I go is all in English. And here in Taiwan, at least for the Institute of Astronomy and Astrophysics, my institute, English is the business language.
Right, yeah.
Yeah.
I guess a lot of the information that we've been talking about today, you can find on the internet, you can find on educational YouTube channels, etc. But where can people find more info on maybe Academia Sinica or what you're doing?
What we are doing, maybe the Academia Sinica Institute of Astronomy and Astrophysics homepage is one good starting point. That homepage has the both English and Chinese explanation for the news. And if more detail, the homepage of the Event Horizon Telescope itself. And of course, the Facebook of the Our Institute or Event Horizon Telescope. And of course, the university like National Taiwan University or National Tsinghua University, they have that big astronomy group. And they also provide a lot of information. So in Taiwan, those kind of research place is one of the good place. And of course, huge amount of, YouTube.
There's so much. And again, so much of it is in English, guys. So study your English.
But some, like black hole, that I saw that within a day or something, that Taiwanese guy made the really good explanation of the black hole in Chinese. So
okay, that's good. That's what we need.
Yeah. So
awesome.
I think Pansai.
Okay, you know what? I'll link to in the podcast description, and we can let people check there. That can be it. Yeah.
Thank you very much for inviting me again. I hope the many people interested in the black hole, and hope we can provide you more interesting results for the third, fourth, whatever results.
Yeah, absolutely. Well, thank you for joining us today, Satoki.
Okay, thank you very much, Trevor.
And thanks to you, the listener. If you enjoyed today's episode, please consider following Taiwan Talk on Spotify or Apple Podcasts or wherever you get your podcasts, and even just share it with a friend. So anyway, that's it for this episode of Taiwan Talk. Until next time, I'm Trevor Tortomasi on ICRT FM 100. If you'd like to hear more from ICRT, you can check out our other podcasts. We've got Taiwan This Week, a roundup of the news in Taiwan every Friday, English in the News for useful English expressions explained in Chinese, and EZ News, spelled with the letters E and Z, for simplified daily news. For some lighter news in both English and Chinese, check out News Bites and News for Kids. And if you enjoy them, tell a friend. Thanks for listening.